Now let's have a look at more questions. Let's prove this theorem. This is called Wolstenholme theorem, and it basically said that he given a prime greater than 3, we have 1 plus a half plus a third all over to 1 to p minus 1 is equal to a fraction, and uh, this fraction is m to n, and m is divisible by p squared. uh it is very hard to directly prove that m is divisible by p squared, but we can first uh look for simple problems. For more easy problem, we first prove p divide m, and this might be very obvious. We can do some algebraic manipulation. We know this is a harmonic sequence, right? And you can see if we can do some, we can regroup those terms. I think you can see it if I regroup 1 and p minus 1 over 1 and 2 a half with p minus 2 over 1, we finally get some very useful information. You can see that every sum after our regroup is divisible by p. And we can say that for the i's term, we pair it with the p minus I over 1 term, and we get that it is divisible by p. And we can essentially regroup all the whole sum using this method, and finally we can prove that because every term is divisible by p, we prove that the whole sequence is divisible by p. And as we know that n eventually will probably be the maximum of n can be p minus 1 factorial. It cannot be greater than this one, because if you expand them out, you will find that the greatest possible factor is p minus 1 factorial, and this is co-prime with p. As a result, we don't need to care about the denominator. We know that the left hand side, p minus left hand side, and we can directly imply that p divides m. But after that, how can we prove another p? Then we want to prove p squared divides m, right? How can we do that? If we continue our observation here, if we continue on this idea, we know that we can write the the equation. We can write the sum like this: p minus I times I, and I equals to 0 all the way to p minus 1 over 2, right? P minus 1 over 2, yeah. This is what we essentially find the left hand side of what we've given, right? And and when the left hand side divided by p, it is here. It is what we've got here. we directly divide it by p. It is very simple. And now what we want to show is that p also divides what we've left with. We can use some properties of modular arithmetic. For example, we can directly use modular arithmetic that we can show that this we mod p, and this whole this should be congruent to minus I square over 1, right? This is greater than this expression because it sounds more concise and more beautiful, and probably we can use something about inverse because the fraction occurs in the modular arithmetic. But we can continue. Now we can first ignore this minus sign because in the end we want to show that the whole congruence equation is equal to 0. So we can ignore this minus sign, now the problem is that in the beginning we have p minus 1 term, and now we only have p minus 1 p minus 1 p minus 1 over 2 term, which is a half of the term as we've seen. But the good thing is we can directly time 2 on this on this structure and to fix this problem. Here's what we can do. If we time 2, what our key insight is that I square is congruent to p minus I square mod p. That's how we turn the first p minus 1 over 2 term into p minus 1 term through multiplying by 2. And it is okay to multiply by 2 because we modulo p and p is co-prime with 2. So if we times 2, we know that we can rewrite it by this, right? I 1 over I squared plus 1 over I squared, and we can rewrite one of the 1 over I squared as p minus I squared, which completes our initial term, our p minus 1 term, and we can directly write it by simply using I square and add over to p minus 1. And this is very beautiful. We start from this and we do some basic property of modular arithmetic. Finally got a very elegant structure here. And what we can perceive is that it's about what we see here. For example, if p is 7, we got 1 over 1 square plus 1 over 2 square plus 1 over 3 square plus over to 1 over 6 square. Does this remind you something? Yeah, we can sum this sequence. We are able to sum this sequence. This is 6 this is a sequence of the first n square, right? It is equal to n times n plus 1 times 2n plus 1 over 6. Yeah. And in this case, our sum is equal to 6 p minus 1 times p times 2p minus 1, right? And this we can see here. Perfect. We know that this is divisible by p, and that's what we are looking for. Now we show that left hand p squared divides left hand side, which implies p squared divide m. So we've completed our proof.